Let's wait for a few seconds for the others to come in. All right, let's begin. So in the last class, we began the series of lectures on how you can learn a network. So what was the problem of learning a network? How did we describe it? Does anybody remember? Anyone? You have a network which is trying to emulate a function. And so we are assuming that the architecture of the network is given. We want to estimate the parameters of the network such that it best approximates this function, except that we don't usually know the function everywhere. So all we are given is a collection of training samples of input and output from the function. And so using the set of training samples, which are basically samples of the function, we try to learn the network that models the function. The way we do it is that we try to learn the network parameters. Again, we saw that the network itself is a function. It's a function both of the input and its parameters. And so we try to learn the network parameters such that for each of these training samples axis, the output is as close as possible to the desired output, D, where D is the value of the function that you're trying to emulate with this network. The way we do it is we define a divergence between the actual output of the network and the desired output of the network. Then we define a loss function, which is the average divergence between the actual and desired outputs of the network at all of the training inputs. And this loss function, since the x's are given and the d's are given, the only variable that remains is this w, which are the parameters of the network. So the loss function itself is a function of just the network parameters. Now, we said that this loss function, is the loss function what we exactly wanted to? What was it we actually wanted to minimize? Anybody?
The expected diversion.
The expected divergence. We wanted to minimize the shaded area, right? The entire shaded area. And this loss is just a proxy of that shaded area, the expected divergence. And our hope is that if you minimize the loss, the entire expected divergence will go down. And so we're going to minimize this loss with respect to the network parameters. This loss is the empirical risk over drawn samples. And this minimization of the loss with respect to network parameters is an instance of function minimization. Given the training samples, the loss is just a function of network parameters. We're trying to minimize it with respect to network parameters. So everybody clear so far? Questions? Okay. So obviously, the problem we're looking at is that of function minimization, or more generally, of function optimization. So let's take a quick detour into function optimization with an initial discussion of what do we mean by derivatives. Does anybody know what a derivative, how do we define a derivative? What is a derivative? Anybody? Instantaneous rate of change, slope, rate of change. Good enough, right? But then Formulaically, here's how you define it. Say I'm given a function y equals f of x. Then at any x, a small perturbation delta x is going to result in a corresponding small perturbation delta x of the input is going to result in a corresponding change delta y of the output of the function. And so the correct way to define a derivative is the multiplicative factor alpha that multiplies delta x to give you the delta y for a small enough delta x. This is, in fact, the only correct way of defining derivatives. And this only holds, obviously, for smooth functions. And it's based on the fact that at a fine enough resolution, any smooth continuous function is locally linear at endpoint. And so the increment delta y is related linearly to the increment delta x of the input. And this multiplicative factor alpha, which multiplies the increment in input to give you the increment in output, is the derivative. So this is the actual definition of derivative. But very often, we just write derivative equals dy over dx. And that's not always right. Why would that be? Anyone? Why would dy over dx not be a good notation for derivatives? Can I pull up a random name and ask? Sometimes dx equals 0. No, the function is not continuous. Multivariate functions, right? If x is multiple variables, you cannot divide. If x is a vector, you cannot divide by a vector. So dy over dx is not a generalizable representation. When x and y are scalar, then if y equals f of x, you can definitely write delta y equals alpha times delta of x. And because both of these are scalar, we can say alpha equals delta y over delta x, or for small enough increments, we write that as dy over dx. So this is a perfectly acceptable notation for scalar functions of scalar inputs. But more generally and more reasonably, you're better off writing this as f prime of x. And there are two reasons for this. First, that this notation assumes that it's a scalar, which may not always hold. Secondly, this multiplicative alpha factor alpha itself depends on where you're trying to compute the derivative. Over here, for example, you expect alpha to be large. Out here, you expect alpha to be small. So the derivative itself is a function of where you're computing it. So it's best represented as f prime of x. And so, as some of you have mentioned, f prime of x measures the rate of change of the function at x. It measures how fast it's increasing with x. And the magnitude basically tells you the sign tells you something about the slope of the function, and the magnitude tells you how steep the function itself is at any given x. So the larger the magnitude of f prime of x, the faster it's increasing or decreasing. But then overall, here's another way of thinking about it. The derivative alpha tells you how much the output y will increase in response to a small increase of the input. And so if you look at this region of the curve, if I increment the input by a little bit, will the output increase or decrease? So what would the derivative be? Positive or negative? Positive, right? Out here, so a small increase in del x is going to result in a decrease in y, correct? So what would the derivative be? Negative. And so the derivative will be positive in regions where the function is increasing and negative where it's decreasing. It's going to be 0 where the function is flat. Now, suppose I have a multivariate scalar function. So x is now a vector. If x is a vector and y equals f of x or y is a scalar, in this case too, I can I can still use the same formula for derivatives. If I increment at any x, if I increment the x a small bit by some delta x, this is going to result in an increase in the output by delta y, increment in the output delta y. And so the linear multiplicative factor that multiplies delta x to give you delta y, that is the derivative. And so here too, you can write delta y equals alpha times delta of x, where alpha is the derivative. Now, if x is a column vector of this kind, what kind of vector will delta x be? Anyone? I need a response, guys. It's going to be a column vector, right? Now, what about delta y? Is delta y a vector or a scalar? Okay. So what can you tell me about alpha then? What must alpha be? What kind of vector? A row vector, right? Because if delta x is a column vector, alpha must be a row vector so that the product ends up being a scalar. And so the derivative of a scalar function of a vector variable, where the variable is a column vector, will be a row vector. And so the alpha is going to be a row vector of this kind with components alpha 1 through alpha d, where d is the dimensionality of the input. And so just writing it out, you can see that delta y can be written as alpha 1 times delta x1, where delta x1 is the increment in the first component of x, plus alpha 2 times delta x2, where delta x2 is the increment in the second component of x, and so on. Now, the increment, because x is a vector, the increment in x can be in any direction, right? So if I modify x such that I increment only the first component and keep all the other components the same, then all the remaining delta x's are 0 and only x1, delta x1 is non-zero. In that case, you're going to get delta y equals alpha 1 times delta x1. So in that, and that multiplicative factor alpha 1 is what we call the partial derivative of y with respect to x1. It tells us how y increments when only x1 is incremented. Or more generally, the partial derivative alpha I tells us how y increments when only xi is incremented. And because now each of these terms is a scalar, you can write it as this ratio term, dou x over dou xi. And so once we've written it in this manner, the increment delta y can be written as the partial derivative of y with respect to x1 times delta x1 plus the partial derivative of y with respect to x2 times delta x2, and so on. Did this make sense? Did all of this make sense? Okay. So we've all heard, so I can write the whole thing like so, right? Instead of writing alpha, we know alpha is a vector. We also know that alpha depends, this derivative depends on the position where you're computing it. So instead, we will use this notation nabla xi. Nabla is this inverted triangle. The subscript x tells you that you're taking the derivative with respect to x, and you're taking the derivative of y. So again, delta y is nabla xy times delta x, where nabla xy is this row vector of partial derivatives. Now, you may be more familiar with the term gradient. The gradient is actually defined as the transpose of the derivative. The gradient, a row vector cannot be compared to a column vector. They live in different spaces. But the gradient lives in the same space as the data itself. And so the gradient is the transpose of the derivative. Now, so we've seen what this derivative is. But do we have any idea of what this derivative really means? So, Yushan, what do you mean by numerator layout? Can you explain? Okay, well, let's skip that question. So does anybody have an idea of what this, so can anybody explain what this thing really is? Do you have an idea? It's a vector, right? What is this vector? It's a row vector of partial derivatives, but then it's not just a slope, right? It has many components, whereas a slope is a slope in one direction. So what is this term? Right. And Sage is correct. So here's how it is, right? I can write for a small enough dx, I can write df of x is the derivative of f of x with respect to x times dx. This is the equation that we just wrote. Dx is a column vector. The derivative is a row vector. The gradient is the transpose of the derivative, right? Now, so the df is a dot product of two vectors, of the derivative vector and dx. So what do we know about dot products? This is a vector in a product, right? So to understand its behavior, let's consider a well-known property of inner products. The inner product between two vectors of fixed lengths is simply the magnitude of the first vector times the magnitude of the second vector times cos theta. Is this equation familiar to you? It is, right? So when is it going to be maximum? If I fix the lengths of u and v. When theta is 0, when the two vectors point in the same direction. And so if this is u, and if the blue vector is v, as v rotates around, here's what the inner product is going to look like. It's going to be maximum when theta is 0, when u points exactly in the direction of v, and it's going to be minimum out here when theta is 180 degrees, that is when u points exactly 180 degrees, exactly opposite to v, right? So now let's go back and look at the equation for the derivative. We said df equals nabla f times dx. Each of these two are vectors, right? So if I fix the length of dx, so I've got this term, derivative term. If I fix the length of dx, then the thing that I can change is its direction, right? When will this term be maximum? Anyone? When dx is the same direction as the derivative, correct? So in other words, the change in the function value is going to be largest if the increment that you take is in the direction of the derivative, of the gradient. Is that making sense? Right? So I'm not sure, there's an alarm that went off. I have no idea. Okay, ignore that, please. So, all right. How do I switch this off? Let's ignore the music. This is not my office. Okay. So what this means is that the gradient, which is the transpose of the derivative, is the direction along x where the function increases fastest. So if this was your function and you are computing the gradient here, this term here, this would be the gradient. This is the direction where the function increases fastest. If you move in that direction, the function increases fastest. And if you move exactly opposite to it, the negative of the gradient, that's when the function decreases fastest. And so, and also we have these other locations where the function is flat, and in those places, the gradient is going to be 0. That makes sense? Okay. The gradient has another property. If I slice the function at some level, the edge that you will get is called the level set. And the gradient is always going to be perpendicular to the level set, the level curve. We won't prove it, but it's something that's very easy to show, and we'll use the fact later. There's also, that just gives us the derivative of x with respect to x. There's also something called the second derivative. We're all familiar with it. When you have a scalar function of a vector variable, the second derivative is called the Hessian, which is a matrix of partial second derivatives. We'll revisit this later in a couple of lectures from now. So anyway, here's our first poll. And let me launch this poll. Can everybody see the poll? Okay. You have 30 seconds. Ten seconds, guys. Okay, let me stop this poll. Let's answer this question. At any location x, there may be many directions in which we can step, such that f of x increases. Is this true or false? True, right? The gradient, the direction of the gradient is the direction in which the function increases fastest. True or false? True. The gradient is the derivative of f of x with respect to x. True or false? False. So if fy equals f of x is a scalar function of an n cross 1 column vector, what is the shape of the derivative with respect of y with respect to x? It's going to be C1 cross n. Perfect. So we got this, right? Now, let's move on. So, the problem of optimization. You're given some arbitrary function and some f of x, which are of some variable x. And the problem of optimization is that of determining where this function is maximum or where the function is minimum. In our case, we're going to be looking at the case problem of identifying where some arbitrary function is minimum. What is the value of x where it takes its smallest value, where the function takes its smallest value. So in a scalar function of this kind, we'd be trying to find this location of x. Or if you had a vector function of this kind, this is the x at which the function is minimum, or what this is the value of x where this function is minimum. And the problem of optimization is trying to find that location. Now, in the case of scalar functions, we know that the function is at a minimum, the function keeps decreasing and eventually flattens, right? And then it begins to increase. So the place where it flattens is where it's minimum. And so you all probably remember from high school that if you want to find where the function is minimum, you simply compute the derivative of the function and find out where it goes to 0. That location is what is called a turning point, because the function goes from decreasing and turns to and starts increasing. So you can find it by trying to identify the x where the derivative is 0, but is this sufficient? So what else do we need to do? Need the double derivative, right? So here is your second poll for the day. This is an easy one. And you're going to have only 30 seconds for it. All right, 5 seconds. All right, let me stop this. Okay, which of these are true? Is one true? 3 is the only one that's true, correct? You're right. And so you want the derivative of the function to be 0 and the second derivative to be positive. Why so? If you have a function of this kind, both the maxima and the minima have 0 derivative because both maxima and minima are turning points and derivatives are 0 at turning points where the function goes from increasing to decreasing or vice versa. So just finding out where the function derivative is 0 is not sufficient. But so this red curve over here plots the actual derivative of the function. And you can see that here the function is increasing until the maximum. If the function is increasing, what will the derivative be? Will it be positive or negative? If the function is increasing, the function is increasing, it's going to be positive, right? So out here in this region, the derivative is always going to be positive. So the red curve is always greater than 0. Then at this point, the derivative becomes 0, right? Then the function is decreasing. So the derivative is going to start becoming negative. And it will stay negative until the function hits a minimum where the derivative has gone to 0. So between this maximum and this minimum, you can see the derivative is entirely negative. And then from the minimum, the function begins to increase, and then the derivative becomes positive. So both maxima and minima will have 0 derivative. But then if you look at the slope of the derivative itself, you observe that when the function is going through a maximum, the derivative is going to go from being positive to being negative because the function is initially increasing and then decreasing. On the other hand, when the function goes through a minimum, the derivative goes from being negative to being positive because the function is initially decreasing and then increasing. And so if you look at the second derivative, the slope of the function itself, at a maximum, the slope of the function is negative. At a minimum, the derivative goes from negative to positive. So at a maximum, the slope of the derivative is negative. At a minimum, the slope of the derivative is positive. In other words, the double derivative is going to be negative at maximum and positive at minimum. And so our usual test is that first, we identify the value of x, all the x's where the function is turning, all the turning points, by setting the derivative to 0. And then you check the double derivative at those x's. If the double derivative is positive, then that value is a minimum, otherwise it's a maximum. All of this is familiar stuff, right? Okay. There's a bit of a caveat. There can be places where the function derivative is 0 and the function is not at a minimum. So, for example, if you have a function of this kind, the slope is 0 here, the slope is 0 here, and the slope is 0 here. So all the locations at which the function is got a 0 derivative are critical points. They can be maxima, they can be minima, or they can be inflection points. Inflection points are where the function is maybe decreasing and then slows down and flattens out and then continues decreasing. Or conversely, the function is increasing and then slows down and flattens out and continues to increase. So in this case, if you look at the derivative, you'll find that at the maximum, the derivative, of course, has this kind of behavior, which goes from being positive to negative. But at this kind of inflection point, the derivative here is negative, it goes to 0, then goes back to being negative. So the derivative is going to have this kind of behavior, right? And at the minimum, the derivative goes from being negative to positive. So what is the double derivative going to be here? The second derivative. Is it going to be positive? Is it going to be negative? What's it going to be at this location? That's going to be 0. And so The second derivative is positive at minima, it's negative at maxima, but at inflection points, it's going to be 0. And in fact, it can be a little more complicated than that, right? It could be something like this, where it stays flat and then goes up. The behaviors can be more complex. What about functions of multiple variables? For functions of multiple variables, the optimum is still a turning point. So the place where the function hits a minimum is where, as you approach that point from any direction, the function initially decreases, and then as you cross that point, the function starts to increase. And so at that location itself, if the function is smooth, the function is going to be flat at the minimum. In other words, the gradient is 0, meaning regardless of which direction you take a very tiny step in, the function value will not change. And so optima are turning points even for multivariate functions. And so if I want to find the optimum of a multivariate scalar function of a multivariate function input, I just need to find the location where the gradient is 0. So here's what we can do. I have a function. I can write out the equation for the derivative, which is a vector of partial derivatives, as you know, and then you can equate it to 0. But then if you equate it to 0, that's not sufficient. You don't know if it's a minimum or a maximum. So now you compute the second derivative, which is the Hessian matrix of the function at the candidate x. And now what is this Hessian? The Hessian is actually telling you the second derivative along different directions. So if you look at the eigenvalues, so if I have a function of this kind, then there are along some directions, the function, for example, look at this guy, right? If I go in this direction, the function increases and then decreases. But if I go this way, the function decreases and then increases, right? So at this point, the Hessian is going to be a matrix with 2 eigenvectors. The first eigenvector will give you this direction. The second eigenvector will give you this direction. It will have 2 eigenvalues. The first eigenvalue will give you the second derivative along this direction. The second eigenvalue will give you the second derivative along this direction. And so over here, what can you tell me about the 2 eigenvalues of the Hessian? What will their signs be? Anybody? One positive and one negative, right? Because as you go in this direction, you're hitting a maximum, but if you go in this way, you're hitting a minimum. So the 2 eigenvalues are going to be opposite signs. If you have a pure minimum, what will the eigenvalues be like at that point of the Hessian? They will all be positive, right? And so you compute to minimize a multivariate function, you compute the derivative, you equate it to 0, you get candidate solutions. You compute the Hessian at that point, and you check its eigenvalues. If they're all positive, it's a local minimum. If they're all negative, it's a maximum. The problem is, solving things in this manner is only possible for some very simple functions. There's an example on the slides. But in the more generic case, it's not even, very often, it's not even possible to write out the formula for the derivative, let alone try to solve for the value of x, where the derivative is 0. So the function to minimize may have an intractable form, or the derivative may be intractable. In these cases, you can't just equate the derivatives to 0 and solve for x. You need iterative solutions. We begin with a guess for the optimal x, and then refine it iteratively until the correct value of x is obtained. So if you have a function of this kind, you'd start off at some initial guess of the minimum and say, I think maybe the minimum is here. So you check the function value and you check, is the function really a minimum here or not? And if it's not a minimum, and how would you know if it's a minimum or not? You can run your tests, check the slope, check the second derivative, right? If it's not a minimum, then you take a step in a direction where the function is decreasing. And then you arrive at a new location. Then once again, you inspect. Is this a minimum or not? If it's not, you take another step and keep doing so until you arrive at a minimum. So you can do this regardless of whether it's a scalar function or a multivariate function. Start at some place, check if it's a minimum. If it's not, take a step and keep doing it until you arrive at a minimum. The questions are, which direction must we take the step in, and how big must these steps be? And so this gives us the approach of gradient descent. So let's say I'm at some point here. Over here, let's say if I'm at some point and if the derivative of the function is negative at that point, what does it tell me? Is the function decreasing or increasing? It's decreasing, right? So at that x, should I be incrementing x or decrementing x? It's a decreasing function. Increasing x will decrease the function, right? So if the derivative is negative, you want to increase. If you want to take a step in the positive direction. On the other hand, if you're in a place like this, where the derivative is positive, will an increase of x increase the function or decrease the function? If the slope is positive. So what do you want to do with x? You want to decrease it, right? So whenever you have a negative direction at some current estimate, you want to increase x. You want to move right to decrease the go lower. Similarly, if the slope is positive, you want to move back in the decreasing direction to go lower. And so here's the trivial iterative algorithm. You're going to come up with some initial estimate, x0. And then at each point, you're going to check the derivative, the slope. If the slope is positive, it means the function is increasing. So you want to take a step back. You subtract a step from the current x. You take a step backwards. On the other hand, if the slope is negative, it means the function is decreasing. And so because the function is decreasing, you want to move forward. You want to increment x by adding a step to it. And you keep doing this until you get to a point where the slope of the function is 0. Is this making sense? This algorithm? Easy, right? I can actually compact that without an if clause. Here's what I can do. I can initialize x, and then while the slope is not equal to 0, I can say xk plus 1, which is the k plus 1 iterate, equals xk minus the sign of the derivative times the step. And you can see why this works. If the slope is negative, the sign of the derivative is going to be, what's the sign of the derivative going to be? If the function is, it's going to be, if the slope is negative, the sign of the derivative is going to be negative, right? And so this negative times negative is positive. And so you'll end up moving forward by a step. You'll end up incrementing x. On the other hand, if the function is increasing, then the slope is going to be positive. So minus of a plus is going to give you a minus. So the net sign is going to be negative, and you'll take a step backwards. So is this making sense? Right. And I can compact this even further. Instead of checking the sign, I can just use the derivative itself. And because the sign of the derivative is actually in the derivative, right? And so I can say xk plus 1 is xk minus some constant step size times the derivative. And so I keep modifying x, updating x using this iterate until the derivative is 0. This is my gradient descent rule, right? Is this making sense? Yeah. So is this step size the same as the learning rate? Indeed it is. That's what we will find out, right? Now, this actually has a little more, it's a little more meaningful than having a constant step size, because here the step is proportional to the derivative. And why is that? Why is having a step proportional to the derivative sensible? For that, say, let me draw a function like this, right? if I have a function like this, out here, the function is steep, right? So am I close to the minimum or far away out here? Far. So do I want to take a big step or a small step? Big. Out here, am I close to the minimum or far away? Do I want to take a small step or a big one? Small, right? You want to be careful. And so where the derivative is large, you want to take a big step. Where the derivative is small, you want to take a small step. And this rule, the gradient descent rule, gives you that property. So let's have our third book. Hmm. Ten seconds, guys. This is an easy one. All right. Let me stop this. Is this first statement true? Yes, there are many directions in which you can step such that f of x increases. Second one, also true, right? The direction of the gradient is the direction in which the function increases fastest. The gradient of the is the derivative of, what about the third one? No, it's the gradient is the transpose of the derivative, right? So anyway, so here's where we are, right? We know that any function at any point, the gradient is the direction of steepest increase. So if you're at some point and you want to update that point to get to a place where the function is more likely to be smaller, in which direction would you want to move the point? Out here. Opposite what? Exactly opposite of the gradient, right? So at any point, moving in the direction of the gradient increases the function fastest. And so you want to go as fast as possible downwards. And so you move exactly opposite the gradient. This doesn't, it has the learning rate. We'll talk more about it in later lectures. So here is the gradient descent or ascent rule for multivariate optimization. To find a maximum at any time, you take a step in the direction of the gradient. To find a minimum, to update your estimate, you take a step opposite the direction of the gradient. This eta is a learning rate or a step size, and exactly what it must be. There are many algorithms for it, which we will talk about in later classes. But here's another thing: when do we stop? So if you follow this rule, the gradient descent rule will keep decreasing your function, right? So you can stop when the eta is the learning rate, this constant here. Okay. So when do we stop? You can stop when the derivative becomes very small, close to zero, or when you find that the change in the function value between subsequent steps is too small. Either of these is a perfectly good criterion to stop your updates. So here's the overall gradient descent algorithm. You initialize your x, and then you iteratively update your x by taking a step opposite the gradient until the function doesn't decrease anymore. So for some functions like these, for nice bowl-shaped functions, gradient descent will eventually always find the minimum. Whereas if you have other ugly functions of this kind, non-convex functions, then gradient descent is going to find the closest location where the function flattens. And sometimes it will be an inflection point. Sometimes it will be what is called a local minimum, a function where the with this little valley, but it's not really the minimum of the function. Or if you're lucky, you can actually get to the global minimum. It could stop at any one of these places. So finally, here's, well, not the final pole, here's the fourth pole. "15 seconds, guys. This is an easy one."
I have a question related to.
Okay, yes, I'll take your question and ending the poll. Which of these is right? C, you want to always take a step exactly opposite to the direction of the gradient, right? So what was the question?
Yeah, I think if I may have missed it, but you explained it that the direction of gradient is the direction of the maximum increase, but how is it intuitive that the direction opposite to the gradient is the direction of least increase?
So look over here. If I move in this direction, I'm going up, right?
Mhm.
Correct?
Yes.
So if I move exactly opposite to it, what will I be doing?
Oh, I see. Okay, makes sense.
Make sense?
Yeah.
Yeah, okay.
Thank you.
So now let's return to our problem, right? So our problem was, after the detour, we were given a collection of training points. We defined a loss function, which is the average of the divergences over all the training points. We wanted to minimize this loss function with respect to argument W. This is a problem of function minimization. And so we can use gradient descent to train neural networks. You would initialize your neural network parameters, and then at each step, you would find the derivative of the loss with respect to the neural network parameters and increment and update them by taking a step, modifying every one of them exactly against the derivative. And you keep doing this until the loss no longer decreases. So is this clear so far? Okay, perfect. I only see 3 yeses. Maybe you guys can give me a thumbs up. All right. So, but then in order to be able to minimize this, perform this minimization, we have to define several things. First, what are these input-output pairs? Second, this function f, which is our network, what is it and what are its parameters? Third, what is this divergence? And so all of these need to be defined for us to be able to perform this minimization. Let's discuss each of them briefly. First, what is function f and what are its parameters? The function, of course, is a neural network, a multi-layer perceptron. We're going to assume that it's directed, meaning it has no loops. It's a network, a directed network where inputs flow in one direction until they come out the other side of the network as outputs. So the network has a set of inputs and a set of outputs, and it has no loops. The parameters are the parameters of all of the neurons in the network. We're going to assume a layered network for simplicity, which means that, as we know, we're always going to have layers, but we will assume simply that all the output neurons are this same layer. We're going to refer to the inputs as an input layer. Now, at the input, there's really no neurons over here. These are just the inputs, but the terminology is to call them an input layer. Then these intermediate guys are hidden layers, and the neurons in the output form the output layer. The individual neurons in this network operate on a set of inputs and produce a single output. And the way they do it is what we saw before. They first compute an affine value of all of the inputs and then apply an activation function to this affine value. to compute the output. So this is how we're going to be describing the individual neurons, though in reality, a neuron can be any differentiable function of inputs and parameters. But the specific format that we will use is the one in this equation here. And so the parameters of the individual perceptrons are the weights and the bias, and the parameters of the network itself are the set of weights and biases of all the neurons in the network. Now, the neuron we said first computes an affine value and puts it through an activation function. So what kind of activation functions will we use? We saw in previous classes that the threshold is not a very nice activation function. So, but there are a variety of other very popular activation functions. For example, the sigmoid, which is given by this, which has the shape of this curve here, given by this formula 1 over 1 plus e raised to minus z. And the derivative of the sigmoid also has a nice formula, which is given out here. The derivative of the sigmoid, if you look at it closely, is going to be 0 initially. It will increase till it gets to this point, then it begins decreasing, and then goes back to 0. We also like using the tanh activation function, which is basically just the sigmoid, but it's sort of scaled so that it's centered at 0. Instead of going from 0 to 1, it's going from -1 to 1. So it's scaled and shifted. So it's a scaled and shifted version of the sigmoid. And its derivative too is going to look like a scaled version of this derivative of the sigmoid. Then you have other activation functions like the rectified linear unit, which is 0 for negative inputs and equal to the input for positive inputs. So clearly the slope of this rectified linear unit is going to be 1 for positive inputs and 0 for negative inputs. And it's not quite defined at this inch. We'll talk about that later. But there's also a smoother version of the ReLU, which is log of 1 plus e raised to z. And this is differentiable everywhere. So this has a derivative, which is the derivative of the smooth version of the ReLU is actually going to look like a sigmoid. And many other forms. Now, these neurons, the way we describe them, are individual neurons where each neuron gets an input and computes an output. And the operation of one neuron does not affect the operation of the other neurons. So what I mean here is that if you look at all of the neurons in the layer, if I perturb the input to this neuron, only the output of that neuron is going to change. These outputs will not change. But you can also have some things called vector activations, which have multiple coupled outputs. So in this case, instead of thinking of these as a collection of neurons where each neuron receives an input and computes an output, you actually have an entire vector block here, which receives a set of inputs and computes a set of outputs. And so what this means is that if I change anything that goes into the into any one of the inputs that goes in here, all of the outputs are likely to change. So to get a better idea, compare these two blocks. In this block, in this one where all the neurons are separate, if I change this weight, only the input to this neuron will change, and so only this output will change. The outputs of these guys will not change. Whereas in this block, because they're all operating together, if I change this weight, every single one of the outputs will change. So we call this vector activations, which receive a vector of inputs and generate a vector of outputs. So is the distinction between vector and scalar activations sort of coming across? It's not like two layers. It's all the neurons within one layer. They just, each one is dependent on everything else. Making sense? Yeah. And so it would depend on the activation. Here's a very simple example, right? This is something that you're using everywhere. It's called, you use everywhere. It's called a softmax activation. So the softmax activation receives many inputs, and it computes a bunch of different affine values. And then the way it computes one output for each affine value. But the way it computes the output is that the ith output is e raised to zi divided by the sum of e raised to zi over all zi. So every one of these affine values is exponentiated, but then they are normalized so that they all sum to 1. So see what happens over here. If I increment this guy will increase. But because they've been normalized and they must sum to 1, if I increment this guy, this increases. So what must happen to all of these? What will happen to those? They will decrease, right? So I cannot just look at this local operation. I have to think of the entire thing as a whole. Modifying one input can change all the outputs. So that's why it's a vector activation, where you have to think of it as a vector of inputs and a vector of outputs. So in fact, even your standard network, you can think of it as vector activations where the individual outputs do not interact. You can think of these as degenerate vector activations. So what we've done is we've defined the structure of the network and the various components of this network. So we've defined the function f and its parameters. Any questions? No questions, okay. So now let's look at what are these input-output pairs. Again, given a set of training input-output pairs, we want to learn a function. So that means, again, this is a mathematical object. All of these must be numerically defined. So each input is going to be some d-dimensional vector. Each target output, assuming that the function actually computes a vector output, each target output is also going to be some multidimensional vector, where the kth component is going to be the kth target output value. But then you have to consider three things. You have to consider the input, you have to consider the target output, and you have to consider the actual output. And so corresponding to each input, there's also going to be an actual output, which is also going to be a vector of the same size as the target output. So I'm just going to call these, I won't go over what the superscripts and subscripts are. You can look up the slides, but is the basic concept coming across? So neurons which have value 0, do they have contributions? If they currently have a value of 0, they're not going to affect the affine value at the next layer, clearly. But then, it doesn't mean that they're going to be 0 for every input, right? So we've sort of come across, we've sort of stated what these things look like, but what values do they contain? Let's consider the input. The input is going to always be, each input is going to be a vector of numbers or even just a scalar if the input layer is of size 1. So it could be a vector of pixel values. Or if you're working on speech, it could be a vector of speech features. Or if you're working on text, it's going to be a vector, a real valued vector, a numeric representation of the text. And we'll see how we can convert text into numeric representations later in the course. But basically, the point is the input is going to be a real value vector, which you somehow derive from whatever data you're working with. If it's images, these are going to be a vector of pixel values. If it's speech, it's a vector of speech features. If it's text, it's a real valued vector derived from the text. What about the output? If the desired output is real valued, then there's no special tricks necessary. The desired output is just going to be a real valued. The neuron itself is going to compute a real valued output. So, and the desired value is also going to be real. If you're computing a scalar function, then the desired value d is going to be a scalar value, and the network will have just one output neuron. On the other hand, if you're computing a function where the output itself is a vector, then the network itself, the output layer of the network will have as many output neurons or as many output components as the dimension of the desired output. And the desired output 2 is going to be simply a vector of real values. So this is easy. If the desired output is binary, for example, if you're performing classification and asking questions like, is this a cat or is this not a cat? Then for the desired output, we can use a simple 1-0 representation of the desired output. Like 1, yes, this is a cat. 0, no, this is not a cat. The network itself is going to have just one output neuron. But typically, in this case, although the output is binary, yes or no, 1 or 0, the activation we will use in this case is going to typically going to be a sigmoid. And the reason we will have a sigmoid is that, as we mentioned earlier, we want our activations to be differentiable, and the threshold function is not differentiable. So this activation will be a sigmoid, and the output of the sigmoid, as we saw in the last class, can be viewed as the probability of the class being 1 for any given input. So this is actually indicative of the fact that for actual data, in general, a feature value x may occur for both classes. So it also sort of captures the semantic that at any given x, you can have, as we saw, you could have the same x value, same input value observed for both output classes. And so, but one class is likely to be more probable for that x than the other. And so the output of the sigmoid can be viewed as the probability of the class given the input x. Any questions? For 3-class classification, here we go for multi-class classification. First, we need to figure out how to represent the output. Now, typically, a multi-class classification is going to ask things like, is this an image of a cat, a dog, a camel, a hat, or a flower? So how do you convert cat, dog, camel, hat, and flower into numbers? You can't, right? So what we will do is to decide on a canonical ordering of these classes. For example, we may say that all of our classes are going to be arranged as cat, dog, camel, hat, flower in that order. Then, for any input which is to be labeled as a cat, our output is going to be a vector which has a single 1 in the position of the cat and zeros for all the other classes. Similarly, any input that's a dog is labeled a dog is going to be converted to a vector which has a 1 in the position of dog and 0 elsewhere, and so on. For each class, that class is going to be converted to this numeric representation, which is a vector which has as many components as the number of classes, and that vector is going to have a 1 in the position of that class and zeros elsewhere. So this is what is called a one-hot vector, because only one component is 1 and all the others are 0. So is this representation clear? So why not use 1, 2, 3, n? How would we use 1, 2, 3, n? The problem is, if you think of these as, if you want to generate a real valued output, then what is 3.7? We wouldn't know, right? So this is a way of identifying every individual class. And to answer, so what do you mean by label encoding? No. We'll get back to why one hot later, but yes, Houston has a very important point. Now, so for a multi-class network with n classes, actually, let me address this point. Why do we use a one-hot vector, or one-hot representation of this kind? So the way we'll do it is, let's say I have 3 classes and I assign them the numbers 1, 2, and 3, as someone suggested. Does this not indicate that these two classes are farther apart than these two classes? Is that not implicit in this? On the other hand, if I have 0, 0, 1, 0, 1, 0, and 0, 1, 0, 0, what is the distance between any two classes? Square root of 2, right? So you're not enforcing any ordering of the classes. You're not saying class A is closer to class B in the absence of other information. That is the assumption we will make, right? If you have additional information, things get more interesting. We'll deal with it later in class. So what do you mean by multi-class, multi-label, where you can have multiple classes in the same time in the data? If I have an image, for now we're going to assume that it's a single class, right? One of these classes. So for a multi-class classifier network with n classes, we will have one hot representations for the outputs, for the desired outputs. The network will have as many outputs as the classes. The network's actual output too must ideally be binary, right? So for any input, it must have n-1 zeros and a single one in the right place. But more realistically, it will be a probability vector, n probability values that sum to 1. So it actually computes the probability for each of these classes. And this is where the softmax activation comes in. The softmax activation computes a number of outputs, which are all positive and sum to 1 and look like a probability distribution. And so for a multi-class classification network, the output layer is going to be a softmax layer with as many outputs as classes, and each output is going to give you the probability of a class. So in the overall setting, you'd be given a number of training data instances like images of digits, along with information about which digit the image represents. And you could have a task which might be either binary recognition, is this 2 or not, or multi-class, which digit is this? So if you had a binary classification problem, your data are going to look like this. You have all of these images, and if your classifier was supposed to determine if the input was the digit 2 or not, corresponding to each one of these, you'd have a label of either 0 or 1. 1 if the input is a 2, 0 if it's not. On the other hand, if you have a multi-class classification problem where you have to find out which digit it is, then along with each input, you would actually be informed which class it was, and that is going to be converted to a one-hot representation when you actually try to train the network. So we have defined the inputs and outputs, and we've defined this function f. But this what we're now left with this last term, which is the divergence. What is this divergence? Now, for the loss to be differentiable, if you want to use gradient descent, you want the loss to be differentiable. That means this divergence function must also be differentiable in addition to the activation function. So the divergence is going to be a differentiable function that is 0 when both of its arguments are identical and always positive otherwise. So for real value output, for networks which are computing real value outputs, the divergence can simply be the popular L2 divergence, which is defined as half of, keep this half in mind, it's going to appear in your quiz. It's defined as half of y, which is the actual vector output, minus d, which is the desired vector output, whole square. So this is the squared Euclidean distance between y and d, which is half of the summation of all components of yi minus di whole squared. This half is here so that when you differentiate it, the 2 that comes out cancels out. Now observe that this is differentiable. The derivative of the divergence with respect to y is simply a vector of partial derivatives, and the partial derivative of this divergence with respect to any yi is simply going to be the error, yi minus di. because this 2 comes out and cancels out. And so the derivative of this divergence with respect to the output of the network is simply going to be a vector of errors. This making sense? DI is the target output, this part of the training data, right? Chetan, that answer your question?
So
Yeah.
DI is the target output, and then Y is what our network will compute.
Y is what the network actually computes. And
Okay.
you're trying to modify
you.
the parameters so that YI matches DI, right? Okay. So that's for real valued outputs. For classifiers, for binary classifiers with scalar output, the desired output D is either going to be 0 or 1. Y is going to be some number. We are going to use a sigmoid activation, so it's going to be some number between 0 and 1, as we saw, right? So you can think of Y as the probability of class 1. And so in this case, you can view this desired output itself as a probability. So when I say, so the way to think about it is, if I say that the desired output is class 1, then I can think of this as this vector 1, 0. Actually, let me erase that. I can. Hey, come on. Is there an eraser here? So if I have 2 classes, and so if the desired output is class 1, I can think of this as the vector 0, 1. If the desired output is class 0, I can think of this as the vector 1, 0, right? And this is like saying that the probability of class 0 is 0, and the probability of class 1 is 1. Here, this is like saying this: the probability of class 0 is 1, and the probability of class 1 is 0. So these one-hot representations actually represent probability distributions. These are desired outputs. So you want the network, when it sees an instance of class 1, you want the network to be absolutely certain that it's class 1 and assign 0 probability to the other classes. So also, when it sees an instance of class 0, you want it to be absolutely certain that it's class 0 and assign 0 probability to other classes. This making sense? Okay. And so, similarly, if this is Y, right? Y is the probability of class 1, right? So this actually represents the distribution 1 minus Y, which is the probability assigned to class 0, and Y, which is the probability assigned to class 1. And so now you can think of this as as being 2 probability distributions. One is Y1 minus Y, and the other is, so again, observe that this guy, I think I have things inverted in my slide. If my desired output is 1, this is the vector 0, 1, correct? So I can write this as 1 minus D, right? And if the vector is 0, if desired output is 0, even in this case, it's going to be the vector 1, 0. And this too becomes 1 minus dt. So this formula holds for both classes, correct? And so I can think of these 2 probability distributions, d1 minus d and y1 minus y. I have the order reversed here. And now I can define a divergence function between 2 probability distributions. And a popular divergence function between probability distributions is the Kullback-Leibler divergence, which is going to be basically, which is defined in this case as d times log y plus 1 minus d times log 1 minus y. And you can see that this is if y equals d. So if the desired output is 1 and the actual output of the network is also exactly equal to 1, then log y becomes 0 And because the desired output D is 0, 1 minus D becomes 0, and the entire divergence becomes 0. Similarly, if the desired output is 0, and the actual output is also equal to 0, then since D is 0, this term goes away. 1 minus D becomes 1. And if the actual output of the network is 0, then 1 minus Y becomes 1, log of 1 becomes 0. So the whole thing becomes 0. So you can see that this divergence term becomes 0 when the desired output exactly equals the actual output. And for anything else, you can show that this is always going to be positive. Now, moreover, here's an interesting thing about the derivative. If you look, I'm going to go a few minutes over, guys. I've been too slow. Yeah, this is the logistic activation. This is sigmoid, right? Now, observe this. Suppose my desired output is 1 and my Y is 0. Do I want to, or Y is like 0.1. Do I want to increase it or decrease it? What happens? If my desired output is 1, then should I be increasing Y or decreasing Y? I should be increasing Y, correct? So if I'm increasing Y, what is the slope of the derivative that wants you to increase Y? Negative. And sure enough, we can see that the derivative of Y when D equals 1 is minus of 1 over Y, right? When D equals 0, what do you want to be doing with Y? You want to be decreasing it all the time, correct? And so you can see that Y is always going to be, no greater than 1. So this denominator is always positive, and so the derivative is always positive. So this formula for the derivative also makes sense, right? Is this making sense? This entire thing? So what was the question? Okay, that question flew by. Ask this in Piazza. Now this has a very interesting property, right? So look at this. Why am I using the Kullback-Leibler divergence and not the L2 divergence? I could very well be using the L2 divergence, right? I could have just been saying Y minus D squared. Instead, I'm using the scale divergence. Now, look at what happens if I plot KL divergence. Suppose I have a target output of D of 0, and the actual output Y is shown along the x-axis. Look at what the L2 divergence has. The L2 divergence is going to be 0 minimum when Y equals D. The KL divergence 2 is going to be minimum when Y equals D, right? But then what is the slope of the derivative of the KL divergence when Y equals D? Is it 0? It's actually going to be 1, right? So look at this. If D equals 0, when Y equals 0, what is the slope? It's 1, right? If D equals 1 and Y equals 1, what is the slope? Minus 1. So, and you can see why this makes sense. This makes sense because from a probabilistic point of view, suppose your target class is 0 and your network says that the output that the class is 1, then it's infinitely wrong. And the KL divergence becomes infinite. And then it comes down very fast as you go towards the correct class, right? And at the correct value, the slope is still 1. Similarly, if the target value is 1 and the network says the output is, the class is 0, it's infinitely wrong. And sure enough, the KL divergence takes a value of infinity and then falls very fast, and the slope becomes minus 1 when it hits the target value. And so simply checking for 0 slope is not sufficient for determining if the gradient descent has arrived. There are at a solution. There are problems where when it hits the minimum, the slope is not actually equal to 0. The slope can be a large positive value. What will happen is that the loss will stop decreasing, right? It's not good that it hits 1 for the slope. It's good that it becomes infinity, when infinity at the other end. The rest is this property. But this has this property, right? So for the binary classifier, when y equals d, the derivative is not zero, even though the divergence is zero. Okay. Yeah, it's because of the law. For multi-class classification too, you can define the Kullback-Leibler divergence in exactly the same manner. Y is going to be a probability distribution. You can think of your desired output D, which is a one-hot vector, also to be a target probability distribution. You want the network to assign 0 probability to all the wrong classes and 1 to the correct class. And so the KL divergence is now defined as the sum over all classes of di times log of di over yi. If you work it out, you can just see that this is summation di log di minus summation di log yi. And if you're using a one-hot representation for the target, then either di is either going to be 0 or 1. And so this term, for all the wrong classes, di is going to be 0, so this term becomes 0. For the target class, di is 1, so log of 1 is 0, so this term becomes 0. So overall, this term is always going to be 0. The second term, for the non-target classes, di is going to be 0, so that they won't figure in this final formula. For the target class alone, di is going to be 1. And so this entire formula is just going to end up with one term is minus of the log of the probability assigned to the target class. That's going to be your KL divergence. Is that making sense? Okay. And once again, if you look at the derivative, so the Kullback-Leibler divergence is simply the negative of the log of the probability assigned to the correct class. And once again, if you look at the derivative of this guy, of the divergence with respect to all the outputs. Now, because only the target class figures, so the derivative is going to have 0 to be 0 with respect to all the outputs corresponding to the other classes. And it's simply going to be minus 1 over yc for the target class alone. And you can see that for the target class, this slope is always going to be negative because y is always positive, right? And so you can see that this derivative is always pushing the probability of the target class to increase, which makes sense. So again, when y equals d, the derivative is not 0, even though the divergence is 0. So have all of these things made sense so far? Okay, so given a set of training input output pairs, we wanted to minimize the loss function. And we have defined the input output pairs, the network and the divergence. So we are set to complete our task. I won't actually ask you this poll, but let's take these questions. The gradient of the loss will always be 0 or close to 0 at a minimum, true or false? The way we defined it. Okay. The gradient may be 0 or close to 0 at a minimum. What about that? Both of these are false, right? So we saw that the gradient may not be false. The gradient is not always, the first one is false, the second one is true. We explicitly saw that at a minimum, the derivative can actually be a strong positive or negative value, right? But in other cases, the derivative can be 0. The gradient of the loss may have a large magnitude at a minimum. It's actually true. If the gradient is not 0 at a minimum, it must be a local minimum. That's a meaningless statement, right? So these are the only two true statements. And so to close, sorry for going over the story so far. Neural networks are universal approximators. They're trained to approximate functions by adjusting their parameters to minimize the average divergence between their actual output and the desired output on training instances, where the input-output samples, training instances are input-output samples from the function to be learned. And the loss is the average divergence over these samples. To train them, several terms must be defined: the network, the manner in which the inputs are represented, the manner in which the output is represented, and the divergence function that computes the error between the actual and desired outputs. Once we define all of these, we can define the laws and perform gradient descent. We will apply this idea to neural networks in the next class. I'll stop the recording here, and with